Uh, all right. Thanks so much for having me. Um, so I'll be talking today about joint work with Angus Lowe, who is a PhD student at MIT. And this was done while I was a postdoc at Northeastern University in Boston. And I'm actually still in Boston, but transitioning to a assistant professor position at Concordia University, which is in Montreal. And I'm looking for students. So there'll also be an advertisement at the end of the talk. So I'm going to be talking today about this is sort of serves as a outline for the talk and also an onion for where the subject of this talk lies. So I'm going to be talking about quantum information theory. Inside of that, entanglement theory, and inside of that, sort of testing properties, entanglement properties of an unknown quantum state. So you're trying to learn. You have some unknown quantum state. You want to learn how or certify that it exhibits some amount of entanglement. And there's lots of variants of entanglement depending on what setup you're considering. And I'll just start my timer so I don't go over. There we go. We're going to be talking today about the particular type of entanglement that shows up in tensor network states, called the bond dimension of a tensor network state. So we're going to be trying to perform quantum measurements to characterize the bond dimension of some tensor network state. And so I'll tell you what all those words mean as we go on. So first, let me just fix some notation, some quantum information notation. So for me, I'll only be considering pure quantum states in this talk. So quantum state for me will just be a unit vector living in some CD tensor n. And I'll refer to n equals 2 case as the bipartite case, like two parties. Think of each copy of CD as being held by some laboratory. And if n equals 2, there's only 2 laboratories. And if n is greater than 2, there are more than 2, and we call it the multi-party setting. So I'm going to use ket1 and ket2 to be the standard basis for C2. So this is ket1 is the vector with a 1 in the first entry and 0 in the second entry. And ket2 is a vector with a 0 in the first entry and 1 in the second entry. And then it's a bit of an abusive notation, but I'll also use ket1, ket2, through ket-d to denote the standard basis for CD. So in this case, ket1 means the vector with a 1 in the first entry and zeros in all the rest of the entries, and et cetera, et cetera. Okay, so let's focus on first the bipartite setting, quantum states. So this is a state living in CD tensor CD. You can think of these as d by d matrices, if you'd like. They're just big, long vectors with d squared entries. You could arrange them into a matrix if you want. Sort of by definition, we define the set of unentangled states or product states or Schmidt-Rank 1 states as the states in CD tensor CD that can be written as U tensor V for some vectors U and V. So if you view this as a matrix, this is precisely the matrices for which the ij entry of that, for which you can find some vectors U and V, for which the ij entry of that matrix is the ith entry of U times the jth entry of V. And this exactly corresponds to being a rank 1 matrix. If you're viewing your state as a d by d matrix, it's a product state if and only if that matrix is rank 1. Okay, and I'm going to use this cartoon for this slide to denote a rank 1 matrix. It's like a row vector times a column vector or product state. Okay. So there's lots of different notions we have. Sort of viewing a bipartite state as a matrix in this way allows us to sort of more easily apply techniques from linear algebra and think of these things as, I don't know, for me it's easier to think of them as matrices than big long vectors. So we know lots of different decompositions of matrices, like singular value decomposition, et cetera. For me in this talk, a decomposition of a matrix will be an expression of a matrix as a sum of rank 1 matrices or a sum of product states. And this is one way to define the Schmidt rank. Yeah, please.
Sorry, just a very dumb quick question. So does this generalize this way of looking at things easily to higher, like if you have 3 systems, for example, does it immediately generalize or is it cumbersome then?
Yes, it immediately generalizes, and I'll show it on the next slide, actually.
Okay. Sorry.
Yeah, no problem. So one way to define the Schmidt rank is the length of the shortest possible decomposition. So the fewest number of product states you need to put in superposition to get your given state. Okay. And there's sort of a canonical state of Schmidt rank R, which is called the Bell state of Schmidt rank R. Okay, and I'll denote it by phi R. And it's just the state that if you view it as a matrix, it has 1 over root r's on the first r diagonal entries and zeros everywhere else. Okay, so here's, for example, 5, 3 living in when d equals 4, living in C4 tensor C4. The first 3 diagonal entries are 1 over root 3, and everything else is zeros. Okay, so we'll call that the Bell state of Schmidt rank R. This whole story generalizes to the multi-party setting, and just for convenience on the slide, I'll set n equal to 3, but you'll see that everything just generalizes very easily to n to arbitrary n. So in this case, we have a big long vector with d cubed entries, right? So we can think of that, we can sort of arrange that into a cube, right? So we can have a d by d by d cube. So we can think of these multipartite states as tensors, what are called tensors, which are these cubes of numbers, or more just higher indexed arrays with multiple indices. And we can define sort of the completely analogous definitions here. So the tensor rank 1 states are also called product states. These are the states which can be written as u tensor v tensor w for some vectors u, v, and w living in CD. Okay, and if we view it as this tri-indexed array, these are exactly the states that can be written as for which the ijk entry is the ith entry of u times the jth entry of v times the kth entry of w. So completely analogous to the rank 1 matrices. And I can use this cartoon to denote a rank 1 tensor, and this is like a column vector times a row vector times a vector coming out of the whiteboard. Is one way to think about it. Okay, and again, we can define sort of the analogous thing, right? A decomposition of a tensor is an expression of a tensor or a multi-party state, an expression of that state as a sum of product states, and we can define a notion of rank, based on this definition. So it's the length of the shortest possible decomposition. Okay, so the fewest number of product states that you need to put in superposition to get your given quantum state. So again, in this case, there's a canonical quantum state of tensor rank R, which is known as the GHZ state. And I'm going to use the same notation. We actually won't encounter this state in the remainder of the talk, but it's worth bringing up. So this is sort of, if you view it as a tensor, as a tri-indexed array, this is the tensor with 1 over root r's on the first r super diagonals. And then zeros everywhere else. So they have the super diagonal going from the top left front to the bottom right back of the tensor, right? The tensor, a super diagonal going through, cutting through the whole tensor there. Okay. Okay, great. So entanglement theory is sort of gives different ways of quantifying how far you are away from the set of product states. So sort of by definition, the unentangled states are the product states. Okay, that's sort of fixed forever. And then there are different ways of quantifying how far away you are from that, but motivated by different operational interpretations, right? So we just saw the Schmidt rank or tensor rank of a state, and we defined it to be the minimum R such that psi is a superposition of R product states. Right, so that's one operational interpretation of the Schmidt rank or tensor rank. And I didn't mention on the slide, but there's another operational interpretation of Schmidt rank and tensor rank, which is as it's the minimum size GHZ state or Schmidt or Bell state if you're in the bipartite setting. So it's the minimum size GHZ state that you need to obtain your given state psi by LOCC with post-selection, okay, which is called SLOCC. So this is another sort of operational interpretation of this measure of entanglement, the tensor rank. There's a million of these, but just mentioned a few. Pseudo entanglement is a computational notion of entanglement being sort of computationally indistinguishable from a state that's far from product state. And then in this talk, we'll be discussing a different notion called the bond dimension as a tensor network state. Okay, it's a different way to quantify the amount of entanglement present in a state. Okay, so this will be, the next slides is defining tensor network states and their bond dimension. Okay, so tensor network states are often called the physical corner of Hilbert space. Because they're made to model the sorts of pure quantum states that can be produced by a quantum computer that's confined to some architecture of interactions between the different qubits, between these copies of CD. Okay, so I'm gonna make this notation. When I write A with an edge between it, so this is like a graph, A with an edge between it with B. This is going to denote the Bell state on CR tensor CR on the sort of laboratory A and laboratory B. Okay, subsystem A and subsystem B. And tensor network states are the states that you can obtain by. So first you have some graph. You start with some graph, and you place Bell states on each of the edges of the graph. Okay, so you can imagine you have some network of like laboratories and like, some of them have connections between them. You're represented by Bell states of rank R. And then after you have these initial connections, what states can you produce, right? So you can just, the E system can just act on her copies of these three Bell states. And Alice can just act on just one copy of this Bell, this half of this Bell state, and Bob can act on these two halves of these Bell states, and Charlie can act on this half of this Bell state, etc. And what states can they produce? This is the data. This is exactly tensor network states. Okay, so in more details, so you start with a graph on n vertices. Okay, so this is an example of a graph on 5 vertices.
Sorry, just a quick question. So you're allowing local operations only. So can they also communicate across the nodes classically, or?
So I'm allowing. It's going to be actually an SLOCC. So
the post-selection thing you mentioned. Okay.
Yeah. So mathematically, it'll be just linear maps on each vertex, which corresponds. So not unitaries, right? So you need post-selection to implement these linear maps. So it's a model for the states you can produce. Yeah. So this is one way to define it, and it turns out that these model sort of if you have a quantum device that has these certain interactions, it's the states that it can produce are well modeled by this set of states. Even though there's this sort of unphysical SLOCC thing in the definition.
Okay. So the unphysical.
Yes. I had a question. So, like this entire tensor network is a big quantum system. It's trying to represent a big quantum system, right? Not wrong.
Yeah, so it's a quantum state. So it's an element of CD tensor. So a tensor network state is a element of CD tensor n. So you define sort of a subset of CD tensor n, specified by a graph on n vertices and a bond dimension R. And so I'll actually get to a more precise definition in a second. So I'll do an example rather. So this might help.
Yeah, I have a question. So what kind of maps are these? Linear maps?
Linear. So just matrices. Yeah. So for example, so let's do this example, and hopefully, if it's not clear after these examples, you can interrupt me again, if that's okay. So so tensor network states are the states that you can obtain in the following recipe. Okay, so first you start with the state with Bell states placed at each edge of the graph, and then you apply linear maps from each vertex to CD. Okay, so for example, like here you'd have like one copy of CR. A has one copy of CR. She'd apply a linear map, so a matrix from CR to CD. The E guy actually has three copies of CR because it has three halves of Bell states, and so it would apply a matrix from CR, tensor CR, tensor CR to CD, et cetera, et cetera. So let's see examples, and then I'll pause for questions.
So this age represents the number of copies, right? If I getting correctly.
A?
So in this network that you have seen, this A, E, so when you say E is having 3 copies, right, of CR?
Yeah.
So this ages represent these copies, number of copies, or I'm missing out something?
Yeah, so I'm thinking of these A, B, C, D, and E as registers that are holding yeah. So the E register is holding 3 copies of CR. The A register is holding 1 copy of CR. The B register is holding 2 copies of CR.
2 copies of CR. Yeah. Okay.
Yeah. Thanks for the question. Yeah. Yeah, it's a confusing definition, and it's very important. So I'm glad that you're asking questions. So let's look at the simplest example where you just have a graph with a single edge, right? So the first step is to consider the state where you place a Bell state at each edge of Schmidt rank R. Okay, so we do that, and then number 2, we apply linear maps from each vertex to CD. Okay, so here there's 2 vertices, so I'm applying 2 linear maps. So I'm applying a linear map from XA and YB. These are both mapping from CR to CD. So these are D by R matrices. Okay. So it's the set of tensor network states of bond dimension R on this graph, the simplest graph, are just the states that you can obtain in this way. You apply a linear map, 2 linear maps on phi R, one on each of the 2 subsystems, and mapping them from CR to CD. Okay.
Okay. If I can ask questions, so these XA and YB, they have to be physical, like they have to map state to state, or are these arbitrarily linear maps?
These are arbitrary linear maps that you could do an arbitrary linear map and then renormalize afterwards, or you could enforce that that when you happen to input, they don't have to map every state to a state, but they do have to map phi R to a state.
Arbitrarily.
Yeah. Yeah.
Okay, got it. Okay, so we have to map. We have to get state at the end, some state at the end.
Exactly. Yeah. Yeah.
Okay. And normalization is so even if XA YB initially are not physical, but since after normalization they can make it physical, so that is okay. We are allowed to act those XA and YB.
Exactly. Yeah.
Okay. Thank you. Yeah.
And you said that one can realize, I'm guessing one can realize these XA, YB by post-selection and classical communication. Is that immediate, that they're equivalent, or is there like a simple way of seeing this?
It's not immediate. Okay, so it can be, the fact that it can be realized. So let's see.
I don't want to distract you from the presentation. I'll take it as a theorem. I was just asking if it's obvious. If it was obvious, then it's okay. We can discuss later.
Yeah, it's not completely immediate, but it's sort of if you're familiar with the fact from that, like the tensor rank, there's this SLOCC interpretation of tensor rank. It's exactly the same argument from there. And yeah, we can discuss after. Yeah.
Okay. Thank you.
Okay, so what you end up getting, okay, so this is a bit unsatisfactory. What are these states that you can get by applying local linear maps to phi R and then making sure, renormalizing? It turns out this is exactly the set of states in CD tensor CD of Schmidt rank at most R. Okay, so it's a very, so sort of in the bipartite setting, when you just have the simplest possible graph, the bond dimension is just the Schmidt rank. Okay. All right. So let's look at the next least complicated example. If there's no more questions about this one.
So Ben, so generalization would so here you're actually taking a bipartite setting. If you're taking a multipartite setting, would that be a hypergraph or something?
No. So this is actually let's see. So this is actually defined. So in the multi-party setting, we're still defining it based on so it's a graph with n vertices would be the n-party setting. So in this case, we have a graph with 2 vertices. So it's the bipartite setting.
Okay, sure.
Yeah, so really only this case.
The edge encodes encodes this tensor of Franka.
Yeah.
In the d dimensions over n planes. Okay, sure, makes sense.
Okay, so here's the next least complicated graph. Right, we just have a line graph with three vertices. Okay, so let's say what are the tensor network states of bond dimension R on this graph? Okay, on this line graph. Okay, so step 1, right? We consider the state with Bell states placed at each edge. So we put a Bell state between A and B, and a Bell state between B and C, and I'm going to sort of keep track of because now B has 2 copies of CR, so I'm going to keep track of those 2 copies and call them B1 and B2. Okay. Okay, so that's step 1, and then step 2, we need to apply linear maps from each vertex to CD. Okay, so what do? We apply, so the A system is just 1 copy of CR, so we're just applying a linear map from CR to CD. B now is 2 copies of CR, so I'm applying a linear map from CR tensor CR to CD. And C is 1 copy of CR, so I'm applying a linear map from CR to CD. So I've written them down here. So X and Z are D by R matrices, and Y is a D by R squared matrix because it's acting on both copies of B, of CR. Okay. Are there any questions about the definition? Okay. So
sorry, so just strictly speaking, you have to have some normalization condition, right? Because the statement you stated, the theorem you stated was that these tensor network states are exactly those, at least in the bipartite case, exactly those that have bond dimension 2 or something. Yeah, exactly. So when you write this equality, you're assuming that TNS is normalized states.
Yes.
Oh, okay.
You're right. Okay. Yeah. So I should have, I guess I should have step 3 should be renormalize the state.
Right. Yeah. Just that. It's minor, but I thought I'd just check the notation.
Yeah.
Thanks.
Yeah, thanks. Okay. All right, so there's different names. We have different names for different, tensor network states on different graphs. Okay, so when you have tensor network states on a line graph, the sort of simplest example,
Hello?
these are called, hi.
Yeah, can you go to the previous slide, please?
Yeah.
Yeah, so since Bob is doing the measurement on 2 systems, so it can create a generally entangled state between A, B, and C, right?
Yes, exactly.
Mm-hmm.
Yeah, so Bob can shuffle around this entanglement that was originally they're uncorrelated here, but then since Bob is doing this is a great point. Since Bob is acting on both B1 and B2, he can shuffle around the entanglement, and now it's no longer going to be product.
Mm-hmm.
Yeah.
So as a consequence, is it true that the set of this TNS for the specific graph that you have across A, B, C, D, E would be the same as the TNS for a fully connected graph?
No, it's not the same. If you have A, B, C in a triangle, it's not the same. Yeah, you end up getting more. That extra edge gives you more.
But couldn't you then? Doesn't the argument that was given that you can create tripartite entanglement across?
No, but
Maybe I
different kind of
misunderstood.
entanglement will be at play.
Okay.
Yeah.
Thank you.
Okay, so we have different names for different different graphs, right? Different tensor network states arising from different graphs. So the simplest case is tensor network states on a line graph. And these are called matrix product states, or actually matrix product states with open boundary conditions. So matrix product state with closed boundary conditions would be a cycle graph. I haven't mentioned those on the slide, but matrix product states with open boundary conditions are tensor network states on a line graph. And these have been shown to be good models for different physical setups, like output of shallow quantum 1D circuits and ground states of 1D local Hamiltonians. More generally, tree tensor network states are tensor network states on a tree graph. Okay, you have a graph. So a tree graph is a graph that has no cycles. Okay, where a cycle is like a closed loop, like that. So these have been used in quantum simulations of molecules. You can kind of see like the tree graph sort of looks like a molecule, and indeed it's useful for simulating molecules, and also simulating ground states of 2D local Hamiltonians. Projected entangled pair states are a really fancy name for tensor network states on a grid graph, and you can sort of infer that these are really the most out of these three examples. These projected entangled pair states are the most relevant in applications because they model sort of a natural architecture. A very natural architecture for a quantum computer, where you have like qubits arranged on a grid, and they can only interact with their nearest neighbors, right? So this sort of models that scenario, and it ends up being very useful for simulating the states that you can produce when you're constrained to some geometry, to this geometry in particular, for your quantum device. Okay.
Ben, sorry, can I ask a question about the previous slide?
Yeah, please.
So just to quickly make sure I'm following. So when for example, the first example with A, B, and C being on a line, so one could do entanglement swapping, right, and have a bell pair across A and C. So my question would be that's correct, right? Like you could make a bell measurement and then you have to do corrections, but I'm guessing since you said that it's equivalent to the model where they communicate and post-select, so I figured they should be able to use, okay, maybe they won't get exactly how many maximally entangled states across A and C as well, but suppose R was like polynomial, like somehow it's like you don't worry about how many copies of environment you have in that case. Like, is that the main difference, that you have only R copies? That's why.
Exactly. Yes. So I think that's a great point. Like if you set R large enough, you can create every state. You can make every state in this way.
Nice.
So if you set R large enough, if you have any connected graph, and you set R large enough, you get every state.
You can simulate it. Yeah. Okay. Got it. Thank you.
Yeah. Thanks. That's a great question. Okay, so we have this class of states, tensor network states, that are good simulations of a lot of several sets of quantum states that can that arise physically. So it's natural to want to quantify the complexity of this set. Right? So let's talk about a few different notions of complexity for this set. So I'm going to focus for most of the talk on matrix product states because they're just easier. So I'm going to define MPSR as tensor network states on. I guess I should index by n as well, the number of vertices, n vertices with R bond dimension R. So these guys, they live in CD tensor n, which is an d to the n dimensional space. But there's a much more efficient description of these matrix product states, right? Namely, you can just write down the linear maps you're applying on each vertex, right? And so what do you need to do? Well, the end vertices, you're applying a linear map from CR to CD, right? And there are two of those. So that's a linear map from CR to CD is described by an R by D matrix. So that's RD parameters, and there's two of them. And then the middle vertices are you're applying linear maps from CR, tensor CR to CD. So that's an R squared by D matrix, and there are n minus 2 of them. So you have a classical description of this size just by writing down the coordinates of those linear maps. And you'll notice that this is now linear in n instead of exponential in n. So it's much more efficient description. Okay, so let's think about some other notions of complexity. You could ask, what's the complexity, the circuit complexity of preparing a matrix product state? Actually, they can be prepared efficiently. This is a result of Vidal in 2006. You could ask, what's the complexity of learning a matrix product state? You have some unknown matrix product state, and you want to determine what it is, right? You want to reproduce, do tomography on the state.
So when you say efficiently, you're thinking polynomial in R and N, or you're fixing R to be polynomial in N?
Yes. Yeah. So, well, I'd have to check. I don't quite remember. I know definitely polynomial in N for fixed R. As R grows, I would have to look. It's still, like, for polynomial sized R, I think it still works, but I'd have to check that. Yeah.
Okay, thank you.
Yeah. Okay, and then there's sort of the complexity of testing membership in MPS R. So say you have some unknown state, and you want to know, is it just a matrix product state of some low bond dimension? Is it an MPS R, or does it have more entanglement than that? Is it like have more complex entanglement? So this is like property testing, and that's the subject of this talk. As we're gonna sort of try develop techniques for testing membership in MPS R and more generally more general sets of tensor network states. Okay.
So for the first 2 points you're given, I think somebody else is also asking. Let them ask because they asked too many questions.
So, so just one quick question before you go to the next one. So you were saying these matrix product states are the tensor network states on a line. So do you is there? I am not aware of this literature. So is there any characterization of all the possible tensor network states for all the possible topologies?
Good. So so we have the definition, right? So but it's kind of it's not very satisfying, right? Because it's like a constructive definite. If you're handed a state, it's not clear that there's some like polynomial time algorithm to decide if it's a tensor network state of some graph of some bond dimension, right? It turns out that for matrix product states and for more generally tree tensor network states, there's a nice characterization which I'll discuss in a bit in the slide. But for general, it turns out when you have cycles, that
Loops,
definition I gave, the definition I gave is basically the best we have. We don't have such a nice characterization. I guess by nice I mean there's probably some complexity separation in, like, I'll show you this characterization and then we can probably talk about how efficient it is to check. But
so in that case, complete graph there will not be a possible also for complete graphs since you are saying that for this loop this characterization is not possible.
Yeah. So actually, for example, if you take the triangle graph, the simplest, so that So deciding if your state is sorry, let me make sure this is right. Yeah, sorry, I was going to say something, but it wasn't right. So yeah, in general, there's no known polynomial time algorithm for deciding if for example, if a state is a tensor network state on a complete graph of a given bond dimension. Yeah.
Okay, thanks. Sure.
Okay, I'll quickly ask my dumb question before you actually explain the result, if that's okay.
No problem. Yeah.
So in the previous slide, the first point, not the first point, because the third point, this the complexity that for preparing an MPS. Sorry, it's the same slide. The third point or whatever third item. So the complexity of preparing an MPS. This I don't know, somehow to me it looks like it's very closely related to the equivalence you mentioned, right? That if you can show equivalence between the two definitions, one being in terms of linear maps and the other in terms of post-selection and communication. Is it because I thought if you gave me the linear maps and I can equivalently find the the whatever corresponding protocol where I'm doing post-selection and communication, that would immediately give me a circuit of the correct complexity. Is that not true?
Well, you have to be careful because that post-selective circuit could have very low probability of doing the right thing.
So that's the non-triviality. So the post-selection might make it complex. Okay.
Yeah.
Okay, thank you.
Thanks. Okay, so now let me describe this testing membership. So I'll kind of take a break from tensor network states for a minute and describe this this primitive in quantum learning theory called property testing, where you're trying to test whether an unknown quantum state satisfies a certain property, in this case being a tensor network state of a given bond dimension with a given graph. Okay. Okay, so the goal is to determine if, so first let me sort of introduce property testing as it appeared classically. So it was before quantum computing was around, people were still thinking about property testing in the general framework of checking if some global object satisfies a property using local queries. So here's a classical example, graph bipartiteness. So you're given a graph and you want to check if it's bipartite. Bipartite means that you can partition the vertices into two disjoint subsets, for which each of those subsets, for each of these subsets, there's no edge going between any of the vertices in the subset. So you notice there's no edges going between these vertices labeled 1, 2, 3, 4, 5, and there's no edges going between these vertices labeled A, B, C, and E. So this is an example of a bipartite graph. And a classical example in property testing is checking if a graph is bipartite using local queries. And what is a local query? A local query is looking at two vertices and checking if there's an edge between them, checking if they're adjacent. Okay, so naively you could just reconstruct the whole graph using n choose 2 queries, where n is the number of vertices in the graph. But actually, it turns out that you just need a constant number of queries. There's a randomized algorithm where you just use a constant number of queries to decide if your graph is bipartite or epsilon-far from bipartite. And this is a randomized algorithm where you literally just check, you take a constant number of vertices and you check all the edges between them and see if you form a bipartite graph with respect to that.
Is that the entire algorithm? Like you pick a random constant sized set of vertices and you just check everything? Is that the...
Yeah, that's the algorithm.
Oh, wow. Okay. Okay.
Yeah.
And
another
also,
example.
Why do we not have a D? Is there like something mysterious happening, or it's just convention? Like the vertex D is... Normally I would have labeled it ABCD.
Oh, I don't know. I ripped this from Wikipedia.
Okay.
I don't know.
Sorry, I thought that was... Okay.
Yeah, good question. Yeah, I was wondering that too. Okay, so another example is probabilistically checkable proofs. These are proofs that you can check just polynomial number of lines of the proof and to certify with high probability that the proof is correct. Okay, so you're doing local queries to certify a global property of being a correct proof. Okay, so let's talk about quantum property testing now. Okay, so a query is going to be a measurement now. So instead of doing a quantum measurement, for the purposes of this talk, a quantum measurement is a positive semi-definite matrix with a maximum eigenvalue at most 1. Okay, and the measurement has 2 outcomes. So the input is some quantum state, and the output is either accept or reject. And the accept outcome happens with probability given by the inner product of psi with p, and the reject outcome happens with the complementary probability. And the state psi is destroyed. Let's just focus on destructive measurements for the sake of this talk. Okay, so this is a natural notion of query access to an unknown state psi. But the measurement destroys the state, right? So each measurement destroys the state. So in order to do n queries, you need n copies of the state, right? Unfortunately, unlike the graph where you can just look at it multiple times, the classical data, for quantum data, you actually need multiple copies of that data in order to look at it multiple times. Okay, and so instead of talking about query complexity, we end up it's called the copy complexity in quantum information theory literature. Okay, so the number of queries you need, we call it the number of copies that you need. Okay. But then, go ahead.
So sorry, but I just have 2 small questions. So one is that, like all these quantum rewinding techniques in quantum crypto that are used, basically where they make some measurement, for witness extraction, things like this. They make a measurement and then they try to undo the damage caused by the measurement. So I'm basically asking if it makes sense, or people have considered looking at post-measured states, post-measurement states as well, and try to see if that is a relevant notion. Or
so in general, there hasn't been a lot of work done on how do I say it?
Like, is it the case that for learning, it doesn't make sense to consider these things, or people haven't looked at it? That's basically what I was trying to understand. I'm not sure it's obvious to me.
Yeah, I would say, yeah, my sense is people haven't looked at it much, but then there's a natural setting called the perfect completeness setting, which is in that case, it's really easy to write down a measurement that is destructive and optimal. I guess, yeah, because in the end of the day, yeah, I would say the answer is probably mostly that people haven't looked at it too much. They're mostly considering like global measurements on psi tensor n.
Okay. And my other dumb question was: is it clear that we look at only binary measurements? Could it be that you could extract some more information? I know you have to make a decision in the end, but potentially having like string outputs in the intermediate steps maybe helps. Is it obvious that's the most general thing to do? Even if you don't consider post-measurement states?
Yeah, definitely. You could consider not just binary measurements in kind of in the intermediate steps. Yeah, but in the end, you have to have a binary measurement. Yeah.
I see. I guess you're just trying to motivate the model that you will actually use. So maybe I should let you continue. Sorry, thanks.
No worries. Okay, so this last point is important. So if you're being given n copies of psi, you might as well just perform a measurement on the entire state, right? If you're, assuming you're assuming that you have whatever computation power you want, you just don't know what the state psi is. You might as well do a global measurement on psi tensor n, because in particular, you could just measure, one example of that is measuring each copy of psi individually. Okay, So this is the setting that mostly is studied in quantum property testing, is when you're doing global measurements. But there are also works that consider, and I'll mention it in this talk if I have time. I'll mention some work where we consider just measuring a few copies of psi at a time. Okay, so in the rest of the talk, I'm gonna just present bounds on the copy complexity of testing tensor network states under global measurements, and also analyze the copy complexity using few copy measurements if there's time. So formally, here's the task of quantum property testing. So we're given a property, which is just a subset of a Hilbert space, okay, calling it curly P. The copy complexity of testing that property is the minimum n for which there is some measurement P on H tensor n, for which every state that is in the property, that has the property, is accepted. Okay, so for every state with the property, it's accepted with probability 1. And for every state that's epsilon-far from the property, I'm using trace distance squared just because it's easier to present the results. But you can use whatever notion of distance you want, and actually the results differ depending on what notion of distance you use. But for all states that are epsilon-far from P and trace distance squared, the probability of accepting is at most 1/3. Okay, so if you have the property, you'll always accept. If you're epsilon-far from the property, there's a high probability that you will not accept.
So I'm guessing for your for every epsilon there exists an n. Is that the way to think about it?
Yes. So I guess I'm fixing epsilon in advance. Yeah.
Okay.
Okay, so let's look at the matrix product states of bond dimension R. I should have a little script R here. So it's known that the copy complexity of testing MPS R is order NR squared. There's an upper bound. This was proven by Solomonofar and Wright in 2022. And then, but there's been this quadratic gap between the best known upper bound and the best known lower bound on the copy complexity, the number of copies you need to test MPS. So Solomonofar and Wright proved initial lower bound, which is later improved slightly by Aronson and others, and Chen and others in 2024. They proved a lower bound of omega root n r plus r squared. And sort of physically, you want to think of n as being large and r as being fixed or growing like logarithmically in n, perhaps. So there's this quadratic gap in n between the best known upper bound and the best known lower bound. So the main result of this talk is of our work is to tighten up this lower bound in some cases. So we prove a lower bound of nr squared over log n, so it's tied up to log factors. But we need this assumption that r is growing at least logarithmically in n. So I have no idea what happens when r is fixed. It could be square root n when r is fixed, or it could be n. I don't know. Okay.
And this is for one-sided error, or is it also for two-sided error?
Exactly. This is for one-sided error. So that's great. So our lower bound only holds for one-sided error. That's another point where our result could be extended. Yeah.
And what's the best two-sided error protocol? Or like, what's the upper one? Do we have anything?
So let's see. I think it's still order nr squared.
Okay.
Because I think if you have any constants here, you can like amplify them.
Oh, okay. But using, often with perfect completeness, there used to be some concerns. I wasn't fully like. I thought you could do 1 minus negligible, maybe, but.
Well, the thing is, if you replace 1 with 2/3 here, right, then that's a weaker requirement, right? So if you're
okay, sorry. Yeah, for the lower bound, it's harder. For the upper one, it's
exactly.
Yeah,
exactly.
Sorry.
Yeah.
Dummy question. Thank you.
No, good question. Yeah. Okay. Are there any more questions about this slide? Okay, great. All right, so let me show you the proof of the upper bound because it's kind of slick. First, so here's this characterization finally of matrix product states of bond dimension R. There's this nice characterization of them. So first, let me note that if you have a state that's a matrix product state of bond dimension R, then it has Schmidt rank at most R for every left-right bipartite cut. Okay, what do I mean by this? So you have your state living in many copies of CD. So you could view it as a bipartite state if you like, right? You could just sort of bipartition these many copies of CD and view it as a state just with respect to that bipartition. So for example, you could look at it as a state in CD tensor, a bunch of copies of CD tensor n-1. And you could look at the Schmidt rank of the state with respect to that cut, right? And you notice that in our definition of matrix product states of bond dimension R, right, we started with a Schmidt rank R Bell state between each of the vertices, and then we applied linear maps to each vertex, right? But those linear maps did not do anything to sort of increase the Schmidt rank between along this edge. So those linear maps, like you can't do anything to the Schmidt rank. You can't increase it just by doing linear maps on the two sides. In order to increase the Schmidt rank, you would have to do something sort of that brings them together. So so it follows that if your state has Schmidt rank, if your state is an MPS R, then it must still have Schmidt rank at most R with respect to this bipartite cut. Okay. And similarly, right, you can do the same thing for all the other edges in the matrix product state. And your state must still have Schmidt rank at most R with respect to all of those edge cuts, okay, which in this case are left-right cuts. And in fact, the converse holds. Okay, so this gives a really nice characterization of matrix product states of bond dimension R. It's just exactly those states that have Schmidt rank at most R with respect to every left-right bipartite cut. Okay. So here's one example. Right, if you start with a state, a bipartite state of Schmidt rank at most R, and you tensor with itself n over 2 times, then this will be a matrix product state of bond dimension R, because you just have to look at all the cuts and make sure that it has Schmidt rank at most R with respect to every cut, right? So if you take a cut, a left-right bipartite cut that cuts in half one of the phis, well, that phi has Schmidt rank at most R, so the whole thing has Schmidt rank at most R. And then if your left-right cut goes between two phis, then that cut has Schmidt rank 1, right? It's a tensor product between those two. So this is an example of a state of a matrix product state.
So if I have, so one of the examples that you're trying to talk about is like saying that if I have a triangle, then I can't do this kind of a partition of like, this is exactly correlating to my tensor rank understanding. But once I have a triangle, I don't know how to put it into the framework. Is it why you do not get any bounds for that?
Exactly. Yeah. So we can't have such a this characterization works when you don't have a cycle. This characterization works. You take all the cuts with respect to all the edges.
Every dimension I'm actually giving it to one vertex, and I'm good here. Every vertex takes one dimension. I mean, one of the n many orders, let's say. Every vertex takes a direction in some sense. It's like, is it what it's happening? Every edge takes a direction.
Yeah. So every edge, when you cut out an edge, it disconnects the graph.
Right.
So it's a tree. Like there are no cycles in the graph. Yeah.
So this must also hold for trees, is it? Or
Yes, exactly. Yeah. Yeah. Okay. Any other questions?
And the example is true irrespective of n, right?
Correct. Yeah.
It doesn't really play.
Okay, so let's get the upper bound. So we need an algorithm that uses order nr squared copies to test matrix product states. Okay, so we have, I just mentioned this result of Vidal and Sirac from 2006 that says that a matrix product state of bond dimension R, should be a little r here, is exactly the ones that have Schmidt rank at most R with respect to every left-right cut. Okay, so actually, let me actually focus on the third line here first. So this is a known result from 2015. They actually characterized the copy complexity of testing Schmidt rank at most R. Okay. So if you have a bipartite state of Schmidt rank at most R, for in the property testing framework, so you're given a state, it either is epsilon-far from Schmidt rank at most R or it has a Schmidt rank at most R. What is the copy complexity? They prove that the copy complexity is both upper and lower bounded by R squared over epsilon. Okay. And so we're going to use this result as a black box. First, I want to mention, actually, okay, so you notice this upper bound we're showing, I haven't mentioned the dependence on epsilon yet. But if you sort of ignore the dependence on epsilon, you can imagine that if you have R squared copy complexity for testing Schmidt rank, and you have matrix product states are the things in multi-party space that have Schmidt rank at most R with respect to each of these n-1 cuts, these left-right cuts, then, well, you can imagine, right? You just need to do that Schmidt rank test n-1 times, right? Just test the Schmidt rank n-1 times. So this is very, very believable that you get this nr squared upper bound, assuming that this r squared upper bound holds for the Schmidt rank testing. Okay. The real story is more complicated than that. So the real story is the following. So hopefully that was clear, because then the real story, of course, will be more confusing. So there's this actually refinement of this result of Vidal and Sirac that says that if psi is epsilon-far from matrix product states, then there's some cut for which psi is, well, epsilon over 2n far from having Schmidt rank at most R. Okay, so not only are these two sets equal, right, but if you're far from matrix product states, then there's some cut for which you're far from having Schmidt rank R. Okay, and there's sort of you lose a factor of n here in the guarantee. And from here, so here's the real proof of the upper bound using O'Donnell and Wright's result. Okay, so you test the Schmidt rank of each left-right cut. It turns out you can actually do this simultaneously. You can actually you can test the Schmidt rank of each cut at the same time. Okay, so when you end up doing
using only one copy of psi?
No, using the amount of copies you would need to test one left-right cut.
Yeah. So I implicitly assumed you did only one. Yeah, but okay. Yes. Okay.
Yeah. Good question. Yeah. So it just turns out that like these measurements commute with each other, so you can actually do these measurements simultaneously. And so, right, with respect to some cut, you're going to be distance epsilon over 2n far away, and so you just plug that into O'Donnell and Wright's result, and you get the bound. Okay, so I've just replaced epsilon here with now we only know that it's epsilon over 2n far away with respect to some cut. All right. Any questions about this this upper bound proof sketch?
So the probability lies in landing in the right slice in some sense. The success probability is like, landing in the right slice. And is there an intuition as to how one can land into the right slice? I mean, the slice at which I have a larger distance.
That's a good question. I don't know. I guess it doesn't really matter for us because you can actually do all these measurements simultaneously. So you can just you don't have to, like, this original the original intuition I gave right before I told you the actual proof sketch was kind of completely wrong because you don't have to test all the left-right cuts. You can just test them all simultaneously, and it's actually just so it's kind of a happy
coincidence,
feeling like we understand something, but it's not actually the reason. Yeah.
So I have a slightly tangential question to this. So here we're talking about, suppose I just talk about Schmidt rank of at most r, somehow it relates to me saying that I'm looking at a tensor of rank at most r in the classical sense. And what is the property testing? I mean, would this translate to the property testing algorithm in the classical sense as well, or something better is known in the classical sense? So because testing rank by itself is an NP-hard question, or like now in existential theory hard.
Yes.
But property testing, so I've not seen the literature of testing tensor rank, for example, let's say.
Yeah, so I mean, we can even just focus on testing matrix rank, right, in the classical setting,
right,
which is still NP hard, right?
Right.
So here, like, we're assuming a computationally unbounded verifier, like we're just allowing them to do any quantum measurement that they want. So it's really different from the classical setting. Because if psi was given to you as a classical state, then you have unbounded computational power in this model, and you can just reproduce the whole state psi because it's classical. Yeah, so it's more information theoretic. These are information theoretic bounds.
Yeah, makes sense.
Yeah, thanks.
I just wanted to mention that we have like about half an hour and you haven't really started talking about your lower bounds. I was a bit afraid. I thought I'd mention.
Okay, thanks. I think it's coming right now. Okay. Okay. Okay, so this is just the definition again. Nothing's changed for property testing. Okay, so proving the lower bound. The first step is to write down the optimal measurement. Okay, so we don't have to search over all measurements. Okay. So what is the optimal measurement? Okay, so say we just fix the number of copies. Like, what's the measurement that's going to satisfy this property, that it accepts everything that's in the property, and it minimizes the acceptance probability of things that are not in the property? Right? This is the question. Okay, well, you need to have, for every psi that's in the property, you need psi tensor n to be in the +1 eigenspace of P. Right? You need number 1 to hold. And then sort of, once that holds, you want it to be like the smallest measurement for which that holds, right? You want to minimize the acceptance probability of every other state that's not in the property. Okay. So it turns out that the optimal measurement is the projection onto the span of psi tensor n as psi ranges over the property. Okay. And this is a nice, this is sort of where I first got interested in this, because I come from sort of trying to apply nonlinear algebra techniques to quantum information theory. And this space is a really nice, well-studied space. You start with a set, you take the span of psi tensor n as psi ranges over the set. This is known as, this is basically the coordinate ring of P, of curly P, in degree n, or you can also think about the orthogonal complement to the ideal of P in degree n. So it's just a really well-studied algebraic space. And anyway, it turns out that the optimal measurement is a projection onto this space. Okay, that's kind of an aside. But
and when you said smallest, could you say again what you meant? I missed it. Smallest measurement.
Yeah. So it's the measurement that is less than or equal to all others in terms of the loner order. So it turns out there is a the set of measurements
TST.
that have turns out there is a minimum element of this set of things that have +1 eigenspace. All these things in their +1 eigenspace, and it's exactly the projection onto the span of those things. Okay. All right. So I probably should have done a slow reveal on this slide also, but basically, you know, like most things, if you're familiar at all with working with multi-party space or with tensors, all we know how to do is working with matrices, and so we just try to make everything we're doing be something in terms of matrices, so we know how to, so we can do some linear algebra. So this paper is no different. Where we're starting with a multi-party setting question, and we're trying to turn it into a question about bipartite states. Okay, so so we're trying to prove the lower bound. So we're trying to prove that there exists a state psi that's epsilon-far from matrix product states, but this optimal measurement still accepts it, right? Unless n is, right, we're trying to prove that n has to be large in order for this not to happen. Okay. All right, so this is the goal with the lower bound. So the first thing I'm going to do is I'm going to basically start breaking things up bipartite into trying to make things look like bipartite. Okay. So I'm going to let Q be the optimal measurement for Schmidt rank. Okay, so this is the projection of the span of phi tensor n as phi has Schmidt rank at most r. Okay. And I want to mention, like, this is the reason why our method only works in the one-sided error setting, is because you have this really nice, you can just write down the optimal measurement. And if you have two-sided error, you cannot, I don't know what the optimal measurement is in general. But for one-sided error, it's really easy to write down the optimal measurement.
So when you say the optimal measurement, you mean it would always accept a yes instance?
It has the property that it always accepts the yes instance,
okay.
and it
rejects at least 1/3.
If you're fixing n, it's the measurement that minimizes that accepts everything and minimizes this. So it's like you can just assume your measurement is this optimal
the
measurement.
smallest. Okay. Sorry.
Yeah.
Thanks.
Yeah. Okay. So I'm trying to bound everything in terms of bipartite things. So the first thing I'm doing is I'm defining Q to be this sort of Schmidt rank optimal measurement. And then sort of, if you recall, right, if you have a state of Schmidt rank at most r, if you have a bunch of states of Schmidt rank at most r and you tensor them together, you're going to get a matrix product state of bond dimension at most r, right? Because whatever cut you take, you either have Schmidt rank r or you have Schmidt rank 1, right? If you happen to cut in between the bipartite states that you're taking. And so that's the reason why this inequality of positive operators holds. Okay, so Q tensor n over 2 is less than or equal to P. Because basically everything that's in, if you take the tensor product n over 2 times of these spaces, these spans, you live inside of this span. Okay, so this inequality holds, and so we can lower bound. We're trying to show that this inner product is large for some psi that's epsilon-far. So we can show in particular that this inner product is large for some psi that's epsilon-far. And so we've turned the measurement into a bipartite measurement, and now we're just going to pick a state that's like bipartite tensor n/2. Right, so that's exactly what we do. We're going to consider a state psi that's of the form mu tensor n/2 for some mu, and then and then we use the So I kind of I'm it's probably hopefully you're getting something from this proof sketch. I apologize, it's a bit opaque. So basically the idea is, we're turning everything into bipartite space. So now we have Q tensor n/2 acting on mu tensor n/2. And then, which is the acceptance probability becomes just the acceptance probability of Q on mu.
And what is
the whole
mu?
thing
Did you
raised
define?
Yeah, so I didn't define mu. It's some state
okay.
that's epsilon-far from that. It's some state that's far from having low Schmidt rank. Okay. Meaning that psi will be far from having low bond dimension as a matrix product state. Yeah. Yeah, so basically we turn it into like testing, like you're applying Q, the optimal Schmidt rank of the tester, to some state mu of high Schmidt rank, and then you're raising the whole thing to the n/2th power, the inner product to the n/2th power. And so it becomes like a question about testing Schmidt rank where the soundness parameter is now 1/3 to the little n/2. And so you have to analyze sort of, how does the Schmidt rank tester work when you decrease the soundness parameter exponentially. And so how does it scale? How does the copy complexity scale when you take this exponent? And you end up working it out and you get this lower bound. This is the idea.
So do you have an explicit psi that is epsilon-far?
Yes. We consider. I think we take as much weight as possible on one on like ket1, tensor ket1. We take as much weight as possible there, and then all the rest are evenly weighted all the way from 2 through D are evenly weighted coefficients. And then we just choose. So there's just basically one parameter that's because of the normalization. There's just one parameter, and we choose that parameter so that mu is the distance that we need. Which I think is so you use you want to choose the distance so that psi is epsilon-far from matrix product states. So I think it would be like epsilon to the 2/n, I believe. Okay. Is there any questions, or hopefully maybe I've lost you on this proof, but
no, I mean I was with you until you the mu part sort of makes sense, that you started with the big measurement and you're writing it as
okay, good.
Smaller Q tensor and
so
I got lost in like the filling.
So if you had to take something away from the slide, it's like saying that there exists a particular mu which is epsilon-far from MPS. That if you work hard enough with that particular explicit mu, and further like mu is giving you psi, if you work hard enough, you can follow the steps through to your proof.
Exactly. Yeah. The main takeaway of this whole proof is that like I'm doing everything. I'm trying to reduce everything to the bipartite case, to some like weird bipartite case where the soundness parameter is going to be weird because like this n/2 is going to now come out of the whole, right? It's going to be it's going to be like bipartite acceptance probability raised to the n/2 is greater than 1/3, and then
so here is Q explicit. Is Q explicit over here? I mean, P and then thus Q, are they explicit?
Yes. So yeah, great question. So yeah, so Q That's a great question, because this span is right. I mean, here it is, right? This is the mathematical description of it, but this span actually might be, in general, if you just have some set and you want to write down the span of psi tensor n as psi ranges over that set, that could be NP hard to write down a basis for that space. But in this case, yes, Q is explicit, and you can write it out in terms of. So you just need to describe this span, this linear space, and you can describe it in terms of using Schur-Weil duality. So this is the set of irreducible representations of of the symmetric group cross the local unitary group, where indexed by partitions of n of length less than or equal to r. So it's exactly all those that have all the spaces that are indexed by partitions of length less than or equal to r.
So I mean, it may not be computationally easy, but you don't care about computational efficiency.
Correct. That's true. It turns out you can actually perform this measurement efficiently, though. So Q can be performed efficiently. Yeah, and also even the
Because I mean, expressing the irreducible representations itself is like kind of like I mean, of course, in classical setting, it's a hard problem, but
yes, yeah. So this is something called weak Schur sampling, where actually, the quantum measurement where you just so without loss of generality, because you have this unitary action, you can just project onto each of the irreps, and then post-select on if you get the irrep with the right where the partition has length less than or equal to r, and that measurement actually can be done efficiently. And you're right; it's kind of surprising that it can be. I don't have a good reason for why it can be. Yeah. Okay. Any other? I think we're probably running out of time. So let me just recap this, what I've said so far. So I showed, so we talked about testing matrix product states of a given bond dimension. And I recapped an upper bound proven by Solomonoff and Wright of order nr squared. And up till recently, the best known lower bound was still, square root n. And they proved this actually using a similar bipartite breakup method, but reducing to a state discrimination argument. Our lower bound, we tighten up this lower bound in the one-sided error setting, assuming that R grows at least logarithmically in n. And we prove it using a similar bipartite breakup method, but actually directly analyzing the error probability.
So does this R show up in the like lower bound and R? I mean, so rather the regime of parameters R that work for you, that shows up in the construction of mu or the construction of the particular epsilon-far.
Yeah. So let me try to remember. I think. So let me mention, we prove a negative result that says if you use this this technique for R constant, for R equals 2, the best lower bound you can obtain is root n, the same as the lower bounds from before. So this method doesn't work, and now I have to remember where it breaks down. I apologize. I don't think I have a good. I don't think I have a good answer off the top of my head. I have to look back at the paper. I don't think it's. I think it's something having to do with like.
If you have to construct as like so state. Yeah. Schmidt rank at most R, yet it is epsilon-far, and the the distance. So there's some play between R and N here.
Yeah.
Yeah, thanks.
Yeah, sorry. I should know. Okay, so it's kind of just really an exercise in so you can extend everything that I've said to tree tensor network states. Any tensor network state on a graph that doesn't have any cycles, like all of this goes through. So one open question is, what is the copy complexity when R is constant? Okay, so we proved that this method, as I just mentioned, can improve the omega of root n lower bound when R equals 2. What about the copy complexity of testing projected entangled pair states and other tensor network states? So the tensor network states on a grid graph, this is completely open as far as I know. So this would be really cool. Another open question that I didn't mention is what is the copy complexity of testing? In the two-sided error setting. That's another question. The best known lower bound in the two-sided error setting is still omega of root n. And okay, so I'll just mention, if you look to the paper, there's sort of analyzing this when you're just measuring a few copies at a time. What is the copy complexity? And there ends up being some interesting connections to, like, oh, if your property happens to be an irreducible variety, then you can write down the optimal measurement similarly to before. It's just like many copies of the same measurement. Yeah, so we have so we prove some upper and lower bounds for that when you have just few copy measurements, and they end up being still independent of D, which is interesting, and also polynomial in N. So it's kind of cool. Like, you can just say R is constant, even when you're measuring just like a constant number of copies at a time, you still have a copy complexity that's polynomial in N and independent of D. So I think that's kind of cool for actually implementing these things potentially. Okay, so I think that's all I have. I just want to mention that I'm looking for graduate students at Concordia. It's located in Montreal, Canada. So yeah, please reach out if you're interested. I'm in the computer science and software engineering department there, or if you know any students who might be interested. So thanks for your time.